Hello, and welcome back to Our Future in Space. I'm your host, Dr. Jeff Greenblatt, the Vice President of Science and Research at Orbital Assembly Corporation. In this podcast, we explore the technical, economic, social, political, and ethical considerations of moving humanity into the solar system to work, play, and ultimately to live. We're at an inflection point in human evolution where we now have the ability to sustain life off planet in low Earth orbit and soon throughout the solar system. Do we merely survive or do we expand outwards and thrive? I'm joined today by my co host, Eric Ward, the Vice President of Engineering Design at OAC. Hey, Eric, good to see you again.
Hey, good to see you too. I'm really excited about our episode today. We're going to talk about computing with Dr. Sadas Shankar, a research technology manager at SLAC National Laboratory and an adjunct professor in materials science and engineering at Stanford University. Dr. Shankar is involved in research in materials, chemistry, and specialized AI methods for complex problems in physical and natural sciences and new frameworks for studying computing. He also worked in the semiconductor industry in areas of materials, reliability, processing, manufacturing, and is a co-inventor in over 20 patent filings. Uh, Dr. Shankar, thank you so much for joining us.
Thank you. Thank you. Glad to
So,
be here.
yeah, absolutely. So, as we're excited about the future of humanity, right? And computing is a really important part of our lives now, and of course, we see that as not going away anytime soon as we expand into the solar system. And so, we're excited to kind of talk about how you see the future of computing in general and for humanity, and how things might change as we expand off the surface of the planet. So maybe to just kind of get everybody up to speed from your perspective, and I know you have a lot of experience in really like how you study computing. How would you say that we as a species are using computing today?
Oh, so that's actually a kind of a very deep question, Eric. I will
Well, so
try
get
to
right
answer.
into it, I guess.
That's a very deep question, actually. In terms of computing, there are many ways of looking at it. It is always illustrative to look at specific quantification to say what we are doing. One way of doing it is the amount of data that is being generated every year. When I say data, I mean digital data. So
Right.
how much of the whole human species, how much have we digitized it? So if you look into internet and all the devices we are using, the smartphones and all that, we are actually at a scale of over 10 to the power 24 uh, number of bits being generated every year. So
Wow.
if you look at the percentage wise, in a certain year, we may be generating more data than the data of the every succeeding a few years combined. And if you just take the last 5 years, the data generated exceed the data since humans have ever produced. So that is an example of how much computing is getting used. Another quantitative way to look at it is the so-called this Moore's law. The Moore's law is over 50 years old. I think it's about 1967. So you can look at it. It's closer to 55 years. So that is the number of transistors on a given area is doubling every so many years. It has been 2 years, and that is about 55 years old. So if you can look at this both these numbers to say that this is actually getting to be almost like the main thing that the whole human uh, system is, the humanity is revolving around computing more so this year than say the year before, because we are doubling the data that is being used.
Right. I mean, so I think you're kind of implying without saying it that these numbers are growing exponentially and in
That's
double
correct.
digit, right,
That's
growth
correct.
every year, 20, 30%. So that's why it's expanding so fast. But I think just to dig in a little more, I think what we're asking is, and I think most people know this, those who use technology every day, but it's infiltrating more and more parts of our lives. I mean, we're talking through digital technology right now in a big way, right? Our voices are being analyzed, compressed, sent through a network, reconfigured in different bit rates, and all kinds of magic is happening, not to mention the video. But what else are we using computing for on sort of an everyday basis? And I'm thinking of things like the everyday AI that we now use on our cell phones, as well as the way we pay for things, and maybe even make basic decisions in businesses. Yeah, maybe you could just give us a quick overview of the kinds of
So that's
ways
actually a very
computing.
nice yeah, that's a nice segue, Jeff. So we talked about the data increasing, and we talked about the number of devices increasing roughly, commensurate with this Moore's law. But it's more than Moore's law. But for the sake of argument, let's say this doubling every so many years. The data is doubling every few months. So these two have actually combined into different kind of exponential curves, one of which is this AI that you mentioned about. So AI can be looked on for people who may not be aware. There are statistical techniques we have always used to interpolate and understand huge amounts of data. That has essentially gone into the next step, what is called machine learning. So machine learning are techniques that we have developed to look at patterns in large amounts of data. Now we are entering a point in which it is called AI, which is mostly unsupervised use of computing to find patterns. So for example, if you're driving a driverless car, the car is probably tracking all the paths you would take and the distance you travel, and it may optimize your travel map for the next day to kind of suit you. Or the radio station you are listening to, the car's radio may actually, unsupervised, may reconfigure stations and suggest stations to you that you want to listen. So this use of AI has been doubling every few months now, the data used. It is being used in applications from what is called natural language processing, trying to translate between languages, trying to find patterns in languages on text. It is being used in drug discovery, materials research, chemistry. It is being used to at least explore new patterns in physical laws based on data. One of the earliest applications of these type of methods has been to detect stars. There has been a lot of data collected in astronomy, but now these AI type methods are helping people identify patterns. So this is kind of changing the paradigm, because there's less and less human involvement when you move into this AI. And that means that all the positives are clear, but there are also negatives that go with it in terms of the mistakes that are being made, or the so-called bots, which are automated things that are in the social platforms that are tracking you and posting things which may not even have humans behind it. So that those are like what you would call like the bacteria and the virus type things on the biology world. You get these other consequences of all these exponential growths that was not originally part of the plan, but is likely to happen whenever you have these type of things growing
So,
at a very large rate.
yeah, so what are some of those kind of unintended consequences of this unsupervised computing? I recall seeing a article a few months ago where they were using AI to do image recognition, and they were trying to train it to identify wolves, and it was doing a great job. But someone went back in later and tried to figure out what the program was actually looking for, and realized that it was identifying wolves based on the fact that almost all pictures of wolves are up in the snow where the gray wolves live, and it was identifying them based on the fact that there was snow there, not any aspect of the actual animal itself. And like that's been, kind of getting me thinking that, as these programs are learning themselves, they're going to come up with solutions that might not be correct or might not be what we intended. So I'm really curious to kind of get into that a little deeper.
Sure.
Yeah. So
Sure.
please.
So this is actually a good topic and a very timely topic. At the very least, you are trying to find patterns in data, right? So you trained it on some data set. They call it the training set or the training data set. And you are trying to, so one way that I'm on the natural sciences and engineering, so I'm not so much of a computer scientist as the one who develops techniques to leverage some of the newer methods. So what the AI is trying to do is, in a way, trying to be a little bit dumb about things that you don't quite know. So you are trying to train it on a complex system's responses. So you are trying to extract causal relationship from correlations. Whenever you do that, even if you did it or I did it, we will make mistakes too. So for example, one example I could say is when the weather gets, when you're transferring from winter to spring in the Bay Area, when the weather gets a little warmer, the number of cars driving north on the Golden Gate Bridge may increase because a lot more people are going up north. They have been kind of staying cooped up. So you got a correlation. So if there is a warmer temperature south of the bay, then there are a lot of people traveling to the coastal towns in California. Now, if there are a lot of people on the coastal towns in California, it doesn't mean that it's warmer south of the Golden Gate Bridge. So I turned around a correlation and made it into a causal effect. This is a problem. We do it, but as humans who are cognitive, we correct for it. We say, oh, there is no vacation. Oh, this is Thanksgiving. So whether it is warm or not, there will be a lot of people going to warmer places. It's nothing to do with the temperature. It's just the season. But AI, let us say you train the AI on the number of days. Thanksgiving happens 2 days a year. So 2 out of 365. So your data, which is 1 out of 180 or so, or call it 0.5%, that is the only data that you have which represents Thanksgiving. So you trained your AI model on the remaining 99.5%, which was not Thanksgiving. So you just extended it to Thanksgiving, but you as a human will correct it, but there's no correction mechanism in AI. And this you could extend it into discrimination, all the human things we do. We put a corrective mechanism. That's what the cognitive part of the brain is. It corrects for things based on context. The problem is AI is not trained on context. AI is trained on data. Now, if you keep adding context to it, then the AI becomes as complicated as the model you were trying to avoid by using AI. So whatever advantage you got, and I can give examples of this from the physical sciences, you have actually now come back to square one. The AI is no longer effective because the time it takes to run an AI is prohibitive. One example I will give you. The number of floating point operations that are needed to train a single 100 billion parameter model on natural language processing these days takes more energy than the top 10 cities in US spend in a month just to train one. And the training takes about 55 days or something. So it's 2 months. It's still taking huge amounts of energy just to train a single model on natural language processing. So now all the advantage you wanted on AI is getting lost. Sorry, Jeff, you had something.
I was just going to interject and say, to be fair, yes, it does take an enormous amount of energy to train this big model, but I just want to ask you, but the benefit on the other side, once it's trained, is that now you can distribute this completed model to perhaps millions of instances, and those run fairly lean, right? And they're saving a lot of time, energy, cost, right? Because if you don't have to hire it, let's say if it's a language translator, if I don't have to hire a personal translator to write a letter for me so I can communicate with my friend in Brazil, then, you know, it's a win, right?
Right.
But
So, I mean, not quite, the math doesn't quite turn out that way. And let me explain why. Now,
okay.
let us say I used such a trained model. It doesn't happen because most of the people don't trust company A having a model versus company B having a model versus you having a model versus I. So everybody has his own model they are training on. Now, once you train it, you just need to run it. So that is called inference. So you are running inference. Now you have to run inferences every second of the day, right? So
Yeah.
if you are having 1 billion operations done per second, a transistor, and you are running it for 31 million seconds, that is the period of number of seconds in a year approximately, then suddenly the number of operations, digital operations you are doing ends up not that far from the energy it took to train it in the first place. Okay, it's still
Okay.
efficient, as you said, but you are
Yeah.
inferring every second. Now, why am I saying it's not efficient? It is efficient compared to training. So you are right. But it's not efficient compared to how you and I operate.
Right.
We spend about 100 watts. That's 100 joules per second. The computing that I explained takes exajoules to train and
Right.
several megajoules to run.
I see.
You're
So in other
saying
words,
that. Oh, go ahead, Jeff.
go ahead. Oh, I was going to say to have I think what you're getting at is with the technology we have right now, the efficiency of our electronic circuits, to emulate something approaching even a fraction of human intelligence, like language translation, requires several million times the energy that it takes a human to just do it. And therefore, it shows us that in nature has found a solution that's far more efficient than what we've been able to build in silicon. Is that kind of where you're going with this?
That is a very good way of summarizing it.
Okay. All right. So might be great, but boy, we're going to be burning a lot of energy at this current rate if we want to use these tools for more and more human applications, right?
Right. Now,
Okay.
the other aspect of it is, one way of looking at it is, if you were to draw the curve of energy usage, which is basically metabolic rate for biological things and energy consumption rates for inanimate systems that humans design, you will find out that computing is one of the more inefficient ones for the amount of energy that is spent. So now let's forget the energy for a second and let's kind of take a step back. What this AI enables you to do is, it at the very least helps you automate things very efficiently. So things that, if the data does not change or the data do not change that much, the training can be done a lot more efficiently. So you can actually be smart about using it, but that may need some sort of human override. It cannot be totally unsupervised like an AI. It is more of the human modulated AI. Then you can
Right.
make it efficient. So it's the best of both worlds, is one thing.
Right. It's a tool, but the way I see it, kind of my context coming from an energy background is, we had a revolution in the available energy per person when we started burning fossil fuels, because prior to that, we had human
Right.
muscle and animals. So maybe each person was, if we were really wealthy, we might have access to 10 kilowatts, which would be like, 20 or 25 horses, right? And a
Right.
single person is like 100 watts, like you said. And now all of us command megawatts of power combine, the electricity that we have command and all the things that we buy and our vehicles and so on. And so we're like on a completely different level in terms of the effectiveness of humans to change the world around us.
Right.
This is now sort of the case with what computation is allowing us to do, it sounds like.
That's right.
Is that a good
That's
analogy?
right. That's correct. But it's not just computing, Jeff, because you have the energy background and you guys are involved in materials. So let's look at an example, right? Each human has like consumes 100 watts, let's just say. You have about 8 billion humans. So you can essentially make a multiplication and say it's 800 billion watts is the power consumed by humans.
Mhm.
So 800 billion. The total energy that's consumed by the humans is of the order of 15 terawatts. Okay. So generally humans consume a lot more energy than the equivalent natural consumption. It's not just unique to computing. And that is why all this sustainability, carbon, and all the problems are coming, because we are generally energetically inefficient. We use a lot of energy. Now, that is the problem is not just energy. The consequences of energy spending means you are generating that much of heat, you are generating that much of chemical products. All of that is essentially kind of the side effects, because if you spend more energy per human, because of these numbers I mentioned, you can actually see we are spending close to 100x what you would naturally consume or our ancestors consume. The interesting part of this is addictive for humans. Why is this? Because energy strongly correlates, more than 90% correlation with the GDP of a country. So the more developed countries are developed because they do a lot more activities which need energy. Industrial production, transportation, I mean, you name it.
And the longer we use it, then we find new uses for energy. And that's kind of what we were getting to earlier, is like, what else are we going to be using computing for today? Like, we're all excited about these new tools that our phones now and our desktops, right, allow us to have, and what we can do in the cloud. But what's coming? I mean, how much more compute, and this is maybe getting to one of our larger questions, how much more compute do you think humans are going to be accessing in the coming years and decades? And maybe we can just try to answer that a little before we turn to the question of, can efficiency be increased? Because just to let the readers know where we're going is, are we going to run out of stuff for building computers in the solar system? That's a question we're actually kind of concerned about, and hoping you can shine some light on today.
So let's try to extrapolate. I mean, I am not great at extrapolation any more than anybody else. So if I have the numbers I have looked at, looks actually that we are on exponential curve for the foreseeable future in terms of our taste or thirst for data. So we are not going to give that up. It is addictive. Everybody wants access to all the data all the time, and we will consume that. So it's the data part. Now comes the other issue that you kind of alluded to, but you need devices. So these devices need materials to be made. So microelectronics, back when I was working at a company, my team was looking at over 70 elements of the periodic table at some point. And this can translate to hundreds of trillions of possible material combinations. If you go into the organic chemical drug industry, their numbers are like 10 to the power 30 chemicals possible, or even 10 to the power 60, which is a gigantic number, more than the number of stars that exist in the universe even. And these means we have the potential to use all of them, but we just don't know how we are going to be able to use it. Why not? Because once we make all these devices, we just send them into landfills and garbage. So it is. So you could ask, why not we take them all out? The entire process of very large scale integrated circuit processes means you integrate huge amounts of transistors. Now they are going into 100 billion range. Some of the new microprocessors are pretty big. You want them in a small square footage or square millimeter. And there all the materials are inside. So even if you plied them all apart, how are you going to separate these materials which are in very small concentrations integrated in compound form? So we take out the gold and expensive other metals, maybe rare earths, but then the rest of it goes into landfill in third world countries. The Western countries send them to third world countries, and there people try to take it apart. This is called e-waste, and then it is just sent into landfills, and you pay those countries to take them, and I don't know what happens to them.
But they're not being turned into new devices in any significant state. You're saying it takes far too much, well, I guess money, but maybe energy too, to
That's right.
re-purify them into their elements.
That's right. It can be done, Jeff, but you need energy. The one good thing is, even in our solar system, we have plenty of energy. So we could make it into 100% circular economy if we wanted. In principle, my brief back
I think we're going to need it, in the long term. We need to be able to recycle those atoms ad infinitum.
So 100% of all the materials could be cycled. So we could have, in principle, 100% circular economy, because they all came from atoms. You could separate them into atoms. You could send them in. In fact, that is what will happen in the future, I suspect. That economy can be funded on energy. We have enough energy to do that. But it needs different kind of thinking. So if you are thinking about space, putting an orbital space station, this is one of the points I wanted to bring up towards the end, but I could bring this up now, is that circularity needs to be part of your design on day one. Rather than waiting to reach the situation that Earth is doing, which is why the solutions that may happen in an orbital type assembly may be very different than what will happen in a terrestrial system with the kind of mineral distributions we have here. The orbital thing may end up with a different mineral distribution because of what your building materials and what access you have. So you may need to do design for circularity going into it, is what I would suggest.
Yeah. I mean, that's definitely something that even on this podcast, we've talked a lot about with different guests is, recycling water, right? You can't just go find an ocean when you're out in the asteroid belt or whatnot. And that, I think even in our talk with Pekka Janhausen, we talked about trying to maintain every atom, right? Rockets, a chemical rocket, sends that exhaust plume out to move around, but then those molecules are now lost to outer space, and his design incorporated ways to move around a massive colony without expending chemical rockets. So, obviously there's this mineral distribution side of things, and, how would we reclaim an old computer that perhaps isn't fast enough, or maybe is not fast enough for the amount of energy it uses, right, to upgrade that technology. How else can we think about circularity when we talk about computing besides just that silicon layer?
So let's so on the Earth, I would say, especially on the Western nations, those of us who are lucky to be on the Western side of things, We actually are a little, how to say, spoiled in terms of our requirements for energy, materials, water, all that, right? This situation will change because of all the climate changes going on. If the water gets redistributed over the world, that some regions of the world will get a lot more water due through rains and monsoons, while some regions are starved. The western side of United States is going into a drought actually again. So then the distribution of water, but then water is not really our problem. So coming to your question, Eric, let's kind of put a hierarchy just to solve this problem in a reasonable way. Let us put energy at the lowest level, then water at the second level, and I will explain why. Then materials at the third level, and then computing as something that interweaves between all of the three. Let's just use this framework to answer your question on circularity. The three things on the left need to be circular for a self-sufficient civilization to exist. You can use finite resources because there are no infinite resources, because water doesn't travel across galaxies. Materials don't, not certainly in enough quantities. Only energy does. So that's why I put energy. So energy makes this into an open system problem. So Earth has no problem in terms of energy supply. We have enough energy from the sun and we can utilize it. But we have problems in terms of water and materials. Now, if you dig a little deep into water also, we don't really have a problem. Why? 70% of the Earth's surface has water. 60% of every human being is water based. In fact, when they do calculations about human density, they use water density because we have so much water. So there is enough water. The problem is, it's not a problem of water not being available. It's a problem of not enough circularity in water. So water problem is circular.
Right.
Material problem is circular. Energy problem is not circular.
So you don't recycle energy very much, right? I mean, you can be more efficient.
Use the energy to solve the other two.
Right.
But
because that comes into the system from an external source like the sun.
That's right.
Yeah.
That's right.
And you can even afford to be, I mean, I hate to say it, but you could afford to be quite profligate with your use of energy because the sun has so much excess, that you could imagine collecting a very large amount of energy and only using a small fraction of it to do things. Obviously, there's a material cost to collecting and concentrating that energy, but you're not looking at an energy constrained society in the solar system.
It is like 1,000 to 10,000x more energy wattage wise we are getting from the sun than we are even using, in spite of all our inefficiencies. So I have presented this before at other places. You can actually use the energy to solve the other two problems rather efficiently. They become essentially a problem of science and engineering. Now, where does computing come in? Computing is the way you chart out those paths of how to do them. And that computers can help. So computing can help, not computers, but computing. So there is where the connection between energy, materials, water is very nonlinear. They are each systems, complex systems. So now we talked about AI, Jeff, early on. What AI is good is in finding patterns between systems not very well characterized. So we can actually use the AI type thing to do what is possible. It may come up with a lot of foolhardy solutions, and maybe there may be one practical solution and 999 useless solutions. It will say, change silicon to copper or carbon to silicon. And then it is talking about transmutation. You don't need to do transmutation. You can intelligently do what it's asking you to do in silicon and carbon. Remember, nature does everything in carbon. Humans do everything in silicon. So silicon is intrinsically inefficient as a mobile platform to do everything because it's denser, heavier, but it's incredibly efficient thing to do computing because it's the second most abundant mineral is silicates on the Earth's crust. Next to oxygen, it's all silicon. So it is great for computation or anything, even for photovoltaic. That's why silicon is very efficient. But it's highly inefficient if you want to create a humanoid because it's much heavier and clunky.
Yeah.
And this is why the robots and all that can never be energetically more efficient than a human. And I have done analysis on this. They are still good for short-term tasks, repetitive tasks, which don't need enormous mobility. Once you bring mobility into it, you need sensing, you need detection, you add all the electronics overload on this, and suddenly your mobile car starts to get dragged down by all the energy and the materials it need.
Right. It's like a whole power plant just to accomplish some
That's
simple
right.
mobility.
That's right. Which we do without thinking.
Yeah.
Right. Drive our 2-ton vehicles around just to go get a bag of groceries and all of that.
Right.
Yeah.
So I wanted to change the focus a little bit to ask, I understand. So let me maybe just make a couple of statements and see if you agree, and then I'll try to get to my question, which is, so we're addicted to computation because of all the positive benefits that it gives us, and that we're showing no sign of slowing down. We're having this hyper exponential growth of computation, and the industry is running to keep up, right? So yes, it's making things more efficient. It's making computation, cheaper. But the point is that this is sort of showing no signs of stopping. And if we look forward even, I don't know, 20 or 30 years, you're starting to look at some real limitations based on what we know how to do today. So I guess my first question is, without a breakthrough, do you see our use of computation as a service kind of hitting a natural wall on Earth? Like basically we would have to, I don't know, mine all the silicon in the Earth's surface in order to build the chips that we need if we're not recycling them, or or cover the entire surface with solar panels to run them, or something like that. Is there a natural limit, and then how do we get around it? That's my first question.
So that's actually a very good question. I'm actually I am working with the Department of Energy on trying to bring energy efficiency into computing. So let's kind of go back into looking at it through the hierarchy of energy, water, and materials. The energy requirement, the way it is currently continuing, is unsustainable. Others have estimated that over the next decade or so, 20% of the electricity generated will be going just into computing. And that is unsustainable because right now it is of the order of 1 or 2%. And if it gets into that number, you are actually not only computing, you are generating all that heat. So you need to have energy to cool it too. So it's doubly additive. It compounds. So energy-wise, it's unsustainable even within this decade, not next decade. Before 2030, it will become unsustainable. Water. These manufacturing of these integrated circuits need huge amounts of water. But a lot of the manufacturing fabs are getting more aware environmentally, and they are recycling water. So water is essentially, we could argue, it's using less water. But if you look into examples like fracking, our recovery, it is consuming huge amounts of water, more amounts of water than possibly, natural gas extraction is using.
Mhm.
Now let's come to materials. If the photovoltaic thing is going to be silicon based, let us say that every roof on the planet is going to have a photovoltaic thing by silicon.
Yeah.
It will compete against the computer, right?
You
On
mean for
this,
the scarce material,
that's
right?
right.
Is that
Because silicon is more scarce. They are actually going and
Mhm.
taking sands, and kind of lands are actually being mined for silicon. Silicon is actually getting to be a problem with the photovoltaic, the PV revolution stepping in. Now, but that's not the only problem, though. You need rare metals and rare earths to do contacts, and the entire microprocessor has silicon only at the base. It's called
Mhm.
silicon technology, but it uses whole new kinds of elements and materials. It takes gallium, aluminum, copper. They all are going to be kind of, they are all limited too. They are all more limited than silicon. If you look in the top 10 available, the things we are using, which includes aluminum, titanium, uh, are two of the elements. We don't use sodium and potassium that much, but those elements all are the only ones we are using in microprocessors. So they are rarer than silicon. Or silicon, you wouldn't call them rare, but they are actually relatively hard to get to. Let's assume we pass all that. But then all this electricity generated need batteries. And batteries have even more complex elements, like you need cadmium, you need nickel. And if you're using flow batteries, you need vanadium. And vanadium is used in construction business. So we will run out of elements, because as we grow, as the whole world becomes as energy intensive as the the more advanced countries, which has approximately between 20 and 30% of the world's total usage. If the rest of the world comes to be like that, then we would be needing 3 to 4 times the materials. I think I'm conservative here. And 3 to 4 times the energy. And that is all unsustainable. So the materials, water is being recycled. Let's assume that we get more smarter on that. The material issue and the energy issue may get to be bigger. And then all the heat generated from all the energy of this computation and this manufacturing needs to be cooled. So it's doubly penalizing and punitive in terms of energy usage. You pay taxes in the beginning and taxes in the end. I'm not federal taxes. I'm saying taxes to the environment.
Right. Environmental taxes. Yeah. So I see that we are kind of coming up against a material limit, at least in terms of what's easily mineable on the Earth's surface. And obviously, we don't want to destroy ecosystems or where people are living. Excuse me, you have to move because we need a mine under your house, things like that. But so I feel like there's sort of one way out, and that would be, well, I mean, up to a point, we could make computation much more efficient, which would, I would say, delay but not eliminate the problem, because if we keep growing exponentially, we'll just hit it a few decades later, right?
That's right.
But maybe before, I mean, realizing that is an eventuality that we kind of have to stop. Maybe 1 gigawatt per person is enough. I don't know, but if let's say we have a huge energy budget like that, in the future where it's really cheap to mine energy from space, how much more efficient do you think computation could get than we're at today? Like, are there some physical hard limits that you've discovered in your work that could point us to, a limit there?
So I can give you some numbers to get context for it.
Okay.
We don't need to go to the outer space to do it, but I have a feeling that efforts which are based on outer space will be more innovative, because they are more constrained and they can actually do a lot more innovation. So let me try to give an example of the limits. Currently, if you look at a microprocessor that was introduced in 2021 or 2022, the energy per switching per transistor is at what is called an attowatt. That is 10 to the power minus 8, sorry, attojoules,
Attojoule.
not watt. Attojoules, which means it is consuming of the order of 10 to the power minus 18, somewhere around that neighborhood joules.
Wow.
If you do a top-down calculation of our brain, a human brain, it would come down into roughly in the same ballpark.
Really?
Yes.
You're saying computing. Go ahead. Yeah, sorry.
So in a way, a company or somebody from a company who makes a microprocessor would come back and say, why are you guys complaining? We are as efficient as a brain, right? So I can do the calculations and show that that's an argument, but it's a little magical argument, because what the brain does, if you do a bottom-up calculation, it is actually 1 order of magnitude more efficient per synapses. So much that. But it is encoding much more information per bit.
Right.
Almost 10 orders of magnitude more information is encoded per a switching in a brain.
Oh, wait, you're saying each neuron encodes 10 to the 10 bits, basically?
So bits in the way you and I define it.
Yeah.
Okay.
Brain doesn't care for bits. Brain wants to make connections. So how does it do it? There is a whole hierarchical process it does. The spike travels around the axon. It reaches the end, what is called the presynaptic version of the neuron. And then some channels opens up, calcium and others cycle back and forth. Then neurotransmitters are packed into vesicles, and they are actually released across the so-called synapses gap. So up to 36,000 molecules of a neurotransmitter is released coming out of one spike. Okay. Now, where is the encoding coming? It does it in terms of quantal vesicles. Nobel Prize was given to the scientist who actually discovered this. And when the vesicles reach the postsynaptic neuron, depending on what chemical was in the neurotransmitter, it has a different signal. So it has encoded information, and there are 90 plus neurotransmitters in the brain, and the number of neurotransmitters. So suddenly it has encoded. So the same switching happens like our transistor, but it has encoded a lot more information.
Right. I think I see. In other words, yeah, it's like a cable that has a whole bundle of wires within it.
If you want to say multiplexing in a loose human sense of the way, it does more than multiplexing, because it is first electrical, then it becomes quantum, then it becomes electrical signals, ion switching, then it does diffusion, it goes into analog, and then it becomes digital again in the postsynaptic neuron. So it has changed informational basis 3 to 4 times in the process of switching. And the architecture gets rewired.
I was going to say that honestly doesn't sound all that efficient. I mean, no criticism of biology, but I guess I'm saying if we're trying to go for an ideal design, should we be imitating this structure, or are you saying this is just telling us how far we are from
getting there?
So that's a good question. So it depends on your vantage point, Jeff. If your efficiency is computational efficiency, that is a valid argument. But if I look at it from energy perspective, this is the most energy efficient way to do it. And evolution was always constrained on energy and materials.
Yeah.
Right. So, as we will be one day too.
That is exactly the point.
Yeah.
Right now, we are worried the way you said it. Computational efficiency is all that matters. I don't particularly care how many bits I waste. In fact, there is a number. It's in a paper that we just submitted, and I can send it to you in a few weeks after hearing back from the review. There's something called bit utilization. Our current computers are 10 to the power 4 to 10 to the power 5 times less efficient in utilizing all the bits that are coming out of the transistors. We need that many more instructions, that many more bits to have a single instruction.
Wow.
While for the brain, it's almost like a single instruction, right? So if you look at it from the bit perspective, it's inefficient. But if you look at it from the instructional perspective, it's orders of magnitude more efficient. So that's where the gotcha is.
That's really interesting.
Wow.
I mean, it seems like very clearly there are some natural limitations and differences between the way a human thinks and the way a computer thinks,
right?
That create almost a boundary box between the two. And I mean, you even mentioned earlier a human-tended AI can be so much more efficient than just a computer,
right? Doing it itself.
Because here the human AI thing. I'm not talking about computer connected to the brain. I mean, I think that's a little bit, I'm not quite bought into that concept yet. But if you are driving the AI like a joystick, you can actually make it a little efficient by not necessarily having the whole search space and configurational space. You could steer it in the right way.
You're guiding,
right?
Using your human intelligence for sort of optimal use, right? And then letting it do the grunt work is the way I see it.
So this may, to some of you at least, this may look like the expert systems that you would have heard in the 1990s and 80s. This looks like that because that's what they intended, but they were way ahead of the times because the computing power wasn't that great. There was not that much availability of data, and they did not have compelling applications to solve real problems. But now if you fast forward 30 years from there, we are in the 2020s now. Some of these concepts could be revisited and kind of changed, modified to suit the times and made into more efficient ways of looking at it.
Interesting.
We're getting a little close.
I did want to ask. Oh, go ahead.
Go ahead, Eric. You first.
Okay, all right.
This is a really juicy subject, so I might just push to stay on a few minutes longer. I mean, I know that we can talk afterwards, Sadas, but in terms of what the viewers, are interested in. So there's one thing that we haven't really touched on in this conversation, which is physical size of circuit elements. And I guess in a way you've sort of maybe hinted at it, but I mean, I guess, let me just ask it point blank, like, is the smallest way to encode a bit in a computational system a single atom? Is that even really possible with the known physics that we have? Or do we really need large assemblages of atoms in order to sort of store or otherwise manipulate bits? And sort of, is it possible on the other end to think of a time when we might be able to manage many bits per atom and kind of, that's no longer a physical limit?
Right.
Energy aside.
So let's take that number that you said, one atom. Let's take the hydrogen atom just for discussion. It's about 1 angstrom diameter, half an angstrom radius, Bohr radius. That is one dimension. But what is smaller than that is the radius of proton. The order of 10 to the power minus 15 meters. So that is at least 5 orders of magnitude smaller. What is smaller than that? Electron. They have not been able to identify any structure to electron all the way to 10 to the power minus 18 meters. Right? So the answer to your question is, what is the smallest physical entity we know? Let's just say it's 10 to the power minus 18. So it's not like you don't have enough margin from where we are today, 7 nanometers to to 10 to the power minus 18 meters, right? So
Yeah.
it's not a shortage of margin. But if you are solving problem at the atomic level, if you're doing information processing at the atomic level, there's another word for that that's called chemistry.
Right.
So your computer, if you're designing a computer, you need to bring in more chemists into the picture because they know how to deal with at the atomic level. Now, if you were to go into a proton is a structure. It's not a single elementary particle. It has 2 up quarks and 1 down quark. That's called quantum chromodynamics. So if you are designing computing, then you need to bring those concepts into it. So size-wise is not the limiting thing, right? In principle, those physics are reasonably well known, even if they are arguing about the interpretations of it. The physics is reasonably well laid out in the standard model of physics. All the way, so from atomic physics to quantum electrodynamics to quantum chromodynamics. So you have the physics going all the way to 10 to the power minus 80. So physics doesn't limit you. But the way the computer made out of these will look differently. So anything at 10 to the power minus 10 should look like a chemical compound or a chemical macromolecule. And that's not the way we design our computers.
Yeah, that's not anywhere close to how we think about computing today. So you're saying it's a completely different design. Not impossible. Nobody said we can't do it, but
that's right.
We don't know what that looks like.
Yeah. So this is largely because different aspects of the physics become the major component of those reactions at those levels versus when you're at the 7 nanometer, when you have some at, I don't know, what's that, dozens, hundreds of atoms per transistor, then you're looking at these more macro physics that are based on what happens with an aggregate of
a lot of the people working on the industry need to retire, and you will have to hire chemists and chromodynamics. But let's kind of so I just made a point that length scale you have enough of headroom.
Yeah.
We made a point most of the podcast that energy is very limiting. Length scale is not. Now let's look at time scale. One of the more recent papers said you could go up to femtosecond or petahertz, that's 10 to the power 15 seconds. You know what happens at femtosecond most of the time? Chemical reaction rates.
Right.
So if you have a femtosecond switch, in principle, the fundamentals of quantum physics, the so-called fine structure constant, which is essentially the conversion between electrostatic and radiation aspects, there are enough known physical principles for you to go up to 10 to the power minus 15 seconds. But then how do you decode the information other than saying a single reaction happened? And how do you integrate it according to your architecture, which is also thermodynamically stable at room temperature?
Right.
Is the problem. It's the
keeping the info discrete is what you're saying.
Encoding
and it comes back to a signal to noise problem, right? In communications, you need to have enough space between individual bits in a transmission at the frequency that you're transmitting at so that you can distinguish a signal from thermal noise, for instance.
Now, after having said that, we kind of tried to say, brain was not computationally efficient. We had a good discussion on that. Now, let me tell you something. A single photon, our eyes can detect a single photon. And in order to have a device that does a single photon, it is still a challenge in 2022. Okay. Including one of the more recent papers that you are aware of, I believe, Jeff. And so nature is doing this chromodynamics, the protons and the nuclei, everything almost routinely. The proton pumps are how ATP molecules are being created in every cell. Humans have up to 37 trillion cells. There are quantum processes in which ATP gets harvested from the energy in mitochondria. There are 50 million ATP molecules being produced in a single cell. Try multiplying that by 37 trillion. All that processing is being done under 100 watts. So I am making the statement, the way we are looking at computing is woefully inadequate for us to look into how a computer in the future can look like. Because we are not using the lessons and abstracting it in the principles either at the architecture level, certainly not at the hardware level. But we understand the physics and chemistry, but we just haven't tapped enough it into engineering. And quantum computing is one such effort, but it has other issues which we'll not go into for this point. Because anything in nature is constantly switching between quantum and classical without almost, it looks to us like no effort. And how are we not able to do that? Why can't we go back from classical to quantum and back? We need to cool things to absolute zero, near absolute zero, to do quantum. How come plants are tapping solar energy and doing photosynthesis?
That's
At
fascinating.
room temperature. Yeah.
Right.
But doing quantum.
Like, is that the issue that we're seeing with quantum tunneling being a problem, miniaturizing our current silicon technology?
So quantum tunneling is a problem in what is called passive power, Eric. When you switch off the transistor, you know that if you close the laptop, you went on a month's vacation, you came back, it would have been drained out of most of your energy. That's where tunneling comes in. Because these devices have gotten so close to each other that even when you turned off, the charge is tunneling. So you need to supply more charge when you turn it on. So the tunneling, you are bringing these transistors down, right? But remember, though, you have hydrogen atoms, silicon atoms, they are all having things in proximity, and they are still performing chemistry with or without tunneling. Sometimes tunneling happens, sometimes it doesn't use tunneling, it's just electrons going out of the valence band into conduction band, and then the unoccupied orbitals. If you're a chemist, it goes from occupied orbitals to unoccupied orbitals, and then it does the transfer and reactions happen. So nature is processing information. It's not like it's all randomly happening, right? Living beings are using this to process information. And so we just need to learn it and use it effectively in a way that we learn not just the fundamental principles, we learn the computing or the information processing examples from nature and use that.
Yeah. Do you think that might result in like biologically like biologic computers, right? The computing run on actual, like cells, or do you think this is more of a let's look at the way that nature has figured out to compute this efficiently and try to make our, hardware technology to kind of run in similar ways or learn those lessons?
Right. The answer to that is actually, you said two options. Its answer to that is both. There are things called DNA computing, in which they use the DNA's its own information processing characteristics to solve a real problem, a logical adder. So that is one in which you are biological computing, right? You are using the DNA to compute.
Yeah.
But on the other extreme, we are not using any principles from biology in our computing today, right?
Yeah.
Between that and biological computing, biologically inspired computing will bridge the two, right? That was the second thing you asked. So second option you are suggesting. So you could have it all of the above. The current ones can extend. We established that length is not the issue. time is an issue because time is associated with energy in quantum mechanics. So if you are switching faster, your energy uncertainties will increase and you need more energy to switch, and all that energy cannot be tapped. Some of it will be dissipated away and you may create heat. That is one issue. Then the other issue is, if you look at the current trajectory of microprocessors since the early 2000s, the frequency of microprocessor is more or less fixed. It's flat. It's not paper flat. It's kind of a relatively flat geometry, which means they don't want it to go too faster than gigahertz. So anything that goes into petahertz, we haven't even used terahertz. And going into a petahertz, people may not utilize it. There may be some application when you want to link it to the optical part of it, when radiation, because terahertz switching, your thermal spectrum happens at terahertz. So you need to go from microwave into shorter wavelength in order to be switching things at the petahertz. So time is a limitation due to multiple factors. Length is not a limitation. Energy is a strong limitation. Material is a big limitation.
Right. The biggest that you
System level
identified.
integration and architecture is a big limitation.
Yeah.
So
you mean being able to actually build these things at such intimate scale.
Right. And the designers, we need different kinds of people.
Yeah.
Not the current designers cannot do that because they're not equipped to handle what.
I mean, they've done an amazing job, but like you say, that we're sort of changing to a different paradigm. We're in the midst of that.
That's right.
Yeah.
So I would love to keep talking about this. We also have
too.
some great questions from the audience, but we are getting up here in time, and maybe we'll have another chance to sort of dive into some of these topics. I think we've really kind of explored what that future of computing could look like, and how that might change as we reach energy limitations here on Earth and expand into new areas in space where we're forced to be a little more circular. I did want to inject one question from the chat before we go. Dean Stephen asks, how could a young person best prepare for a career in this the edge of computing and programming for these really cutting edge applications?
So the answer to this question is simple in one way and complicated to implement. So I will give the simple answer. Everything we have discussed in terms of physics, chemistry, and all is at least 20 to 30 years old. Nothing has changed.
Yeah.
Quantum chromodynamics, standard model of physics, nothing has changed. So chemistry, even older. So if you want to look at computing, so what about the computing side of things? A lot of new innovations are coming in algorithms and machine learning and all that. But the statistical methods on which those algorithms of machine learning are being used, they haven't changed that much. They have been made better. So my suggestion to younger people is get your fundamentals right and stick close to the natural sciences and engineering. That will not get obsoleted. If you jump into something like the AI of today will look very different from the AI 10 years from now. I will give it to you in writing. That will look very different. The computing 10 years from now may look very different. But the physics, chemistry, and biological aspects that I discussed, they will look more or less the same, I think.
Yeah.
So then that answers the question.
Oh, fantastic. Thank you. Well, I think that's just about all the time we have. So, thank you so much for coming and talking. And thank you, of course, for everyone who joined us live and asked some questions. For anyone listening, of course, as usual, if you have any suggestions for future discussion topics or people that you'd like to interview or just want to reach out and be part of the conversation, feel free to contact us. You can always send us an email at ourfutureinspace@orbitalassembly.com. And we're on Twitter at Our Future Space and Facebook at Our Future in Space.
Thank you.
And if you like what OAC is doing and would like to find out how you might be able to contribute in other ways, feel free to reach out to us at info@orbitalassembly.com. So with that,
Yeah.
Sadas,
Thanks for listening,
anything you
and
want
thank
to
you,
say?
of course, Sadas, for joining us.
Thank you. Thank you.
All right. Have a great one, everyone. Bye-bye.